Computer Science and Engineering at IIT Goa. She received her MTech and PhD in Electrical Engineering from IIT Bombay. Before joining IIT Goa, she was a postdoctoral fellow at Robert Bosch Center of Cyber Physical System at IISc Bangalore and a research scientist at IIT Bombay, where she worked on the development of indigenous Ajit microprocessor. Her research focuses on modeling, simulation, and optimization of discrete event systems with applications in computer system design, networks, and digital twins of industrial and manufacturing processes. She develops frameworks for parallel discrete event simulation and for hybrid discrete continuous system simulation. She serves on the ASEAN India Education Committee and is a senior member of IEEE. Over to you, Ken.
Hi, thanks for the introduction. So hi everyone, I understand it's after lunch, so I tried not to make this talk very boring, it will be short, and if there is some question, feel free to just raise your hand, okay, even in the middle of the talk, it's alright. It's not a very long talk, so I can take questions in the middle of the talk also. So, my area of work is in discrete event systems. Particularly, I build simulation frameworks that are scalable and for hybrid systems and so on. So what's going to be there in this talk? Okay, this is a gentle introduction to discrete event simulation. For those of you who may not be in that area, maybe some of you have used this. So what is exactly discrete event simulation? How does it work and so on? Parallelizing discrete event simulation. Why is it important or is it necessary? How can we do it? Okay, and something about a framework that we have built over the years. It's a project that started long ago, so it's not the current thread of work. We have finished this, but we have just recently published some papers on it. So it's a simulation framework we have built, so I'll share some key ideas and some results. And since many of you here are aspiring PhDs, how many of you are already PhD students? Okay, I think many are maybe considering PhD, so some ongoing research threads that may be of interest. Feel free to just meet me if you're interested in any of these threads. So in systems research, right, modeling and simulation is important. Why is it important? Often we are dealing with systems which are complex, which are consisting of many parts that are working together. And it's not obvious what will happen in future if we know the behavior now. If we had a nice analytical formula, or if it was obvious, we wouldn't need simulation, right? So we do need simulation in systems research, and often the systems we are dealing with are big, they are quite complex, and we are interested in predicting what would happen later, what would happen if we tweak the system a little bit, what would happen if we remove a component and so on. So we are interested in all these what if analysis. We are also interested in if what analysis. What kind of a tweak to the system would optimize the performance, for example. Both kinds of questions, right? And how many of you have used any kind of simulator, either in electrical engineering or computer science, architecture, VHDL, Verilog, System C, circuit simulators? Most of you have used. Okay, great. Just to be on the same page, you all agree there is a difference in modeling and simulation, right? So what is a model? All of these are models. What is a model? What is common to all of this? Even a 3D model or a toy train is a model. It's a representation of some real system that abstracts some aspects and ignores some others, right? For example, you may mimic the shape and the size and ignore the functionality, or only focus on the functionality and ignore other aspects and so on. So this is a model. So what is simulation? Anyone? Okay. We make it work, exactly. So something to do with running it, right? It's a kind of a verb, right? Simulation, to simulate something. So if you see, if the real system is a plane, it could be a physical model, it could be an analytical model, but some of the models are simulation models. Not all models are simulation models. So what exactly is simulation? So it involves something to do with time. If there is no time axis, often we call something simulation, but typically it is used for something where there is a time axis, right? So essentially, we know the system behavior at the beginning and the state, and we want to see how the state evolves over time. So there is a time axis, and we know the sort of equations that govern the behavior or what happens in every step or something like that, right? and then we actually run it ahead in time to see what happens. So this is simulation, and roughly depending on the type of the system, so essentially you have some time variable t, some state variables, and then while some time we update the state and increment time. Essentially something like this is simulation, right? So if a system is static, there is no time axis at all. Let's say what is the steady state output in a circuit, for example. There's no time axis required. We are interested in what happens over time. So it's a dynamic system. Or a system may be deterministic. Every time everything is given, you get the same output. Or it may be stochastic. So we have purposely added some randomness to mimic reality, and every run gives a slightly different output, and we are interested in the distribution of how the output is or the system behaves, right? So for all these combinations, some of these make sense to call them a simulation, right? So if the system is dynamic, typically this is called a simulation. Sometimes even Monte Carlo methods are, for static models, we call it simulation. So we are interested typically in stochastic simulation models. These are models in computer architecture, networks, electrical systems, and so on. So you must have heard of continuous and discrete event models, right? So what exactly is discrete in a discrete event system? So this is the question, is it the state space? That means the number of states that are possible is a discrete set, is it that case? Or is the time instant values discrete? That means things can only happen at integer time values. Or the third one, what do you think? State space is discrete? How many of you feel the second one? How many of you think the third one? So actually it's the third one. The state space, well, depends what you can see. If a robot is moving, for example, it's moving from here to there, it's a continuous space where it can be. Its position is a state. Time instant values, right, the delays, etc. in the system can be floating points, can be real valued. It need not be integers. Actually, discrete event system means an instant where the state changes is called an event. Okay? So the set of all these events, whenever the state changed, if you look at it, if you look at it, it's a discrete set. So here's a system where some temperature, etc. is changing over time. If I ask you, tell me the time exactly at which the state change, you say, oh, I can't. It's a continuous. It's changing continuously. Whereas in this system, maybe it's a queuing system. Maybe somebody's entering, somebody's leaving. Every such change in the system is an event, and you can point out precisely the instance when it changed, and it's a discrete set. Here is a continuous set. It changed continuously over all of this time. So what happens is typically some systems themselves are continuous. Let's say weather models. When did the weather change? It's continuous, right? Or temperature flows, etc. And we describe them using differential equations or systems of PDEs, ODEs, or DAEs, and so on. We describe what happens to the system. But then computers are discrete. States are discrete, time is discrete. So we use some sort of approximation, discretize it, and do the simulation. The other case is the system itself is discrete event. For example, at an airport, a flight arrives. We don't care about the flight actually arriving slowly and hitting the runway. We can say the flight arrived at time 12:05. Okay? So, or a restaurant, a customer arrived, customer left, or a computer system where an instruction was decoded. Right? We are at what clock cycle? So we can ignore continuous nature of things, and we can approximate the things to be discrete event, or the system itself is discrete event. For example, a computer network, things are happening on a clock cycle. Okay? Or in a digital system, for example, everything is happening on a clock cycle. So the system inherently is discrete, or we approximate it to be discrete. And how do we typically describe these systems? So at the beginning, what is the state? And every component of the system, maybe we describe the behavior as what will happen in some time. So we say, okay, some delay, and after that delay, what will happen? And the event could be something that changes the state, or it could be something that triggers some change on the neighboring components and so on. Okay, so everybody okay with what is discrete in a discrete event system? So I hope this is okay. So some examples where you use continuous models, right? Flow simulations, heat flow simulations, system dynamics, electromechanical simulations. These are a cross section of a motor, weather simulations, tsunamis, and so on. Some places where the models are discrete event, computer networks, okay, computer architecture models, you have memory and blocks and so on, it's a pipelined model. Digital systems, queuing systems, any kind of systems where there are people entering, leaving, like in an airport, what should be the benefit of having another counter for checking? How much queuing would reduce and so on, these kinds of questions. Queuing networks, manufacturing systems, and so on. So essentially, how do we simulate? If you have all used some sort of a simulator, you might have thought about how the simulator works, right? So what are the essential ingredients? Anyone? If you were to write a simulator of some system that you're using, run button, okay, GUI, excellent. That's how it will interact with it. Some way to describe your model, right?
System property.
System properties, okay. What is the behavior of the system? How does it evolve in time? If you had an analytical formula, plug in T and X, whatever you get the output, you won't need a simulator. You need a simulator, so that means it's not obvious how it will evolve. You need to run some program. So typically, what are the ingredients? Some way to describe the model, what is being. If the circuit simulator, you will say, okay, my circuit has this things connected, there's a resistor, there's an inductor, and so on. Or if it's a computer model, you will say, okay, this is a memory and so on. Some way to describe the system, some way to describe what should be the behavior, how it evolves over time. Then some state variables, right? Those are actually changing over time. A time variable, and this behavior encapsulated as a function, which you will call, right? Some sort of a state update function. So you'll have some state variables, and if you use object-oriented programming, if let's say there's one part of the system, you will club all of those variables into one object, right? Meaningful, something that is meaningfully one object. So we divide our complex system into lots of objects. May help in the modeling also. We describe the class once and instantiate it many times, right? So we have objects, we have a time variable which we will advance, initially t equal to 0. We have a state update function. When you call the state update with some delta t, what should happen to these state variables? And we have a scheme for advancing the time, right? So essential ingredients. So how do we advance time? So there are these broadly two classes of approaches. It's not a very complicated diagram. It's just a, don't worry about it, looks complicated, but it's just a way of advancing time. So here, A, B, C may be some objects in the system. They are all existing simultaneously. Maybe there are some blocks in your block diagram. A, B, C are some parts of your system. Okay. And this is the time axis, top to down, top to bottom. And the purple things show some state updates being executed. Okay. So in continuous models, what we do is we choose a small delta t, which is small enough, and execute all the parts, some run function on ABC, which may change the state of ABC or change the state of its neighbors or something like that. And then we increment time to delta t, do it and so on. So very straightforward. Sometimes we may change the delta t, but still when we change it, it's the same value. We know what is delta t. We know what is the time when these things are running. This is called a time stepped approach. It's a very obvious way. The other one is called the event driven approach. So this is kind of like taking shortcuts in time, and a lot of the modeling frameworks actually use the event driven approach. So how many of you have used VHDL or Verilog or System C? So they use the event driven approach. Okay. What happens is ABC might be objects in your system like wires, okay, that store the state, and you have a large queue which is called an event queue, where you store events that are scheduled for future, sorted by the time at which they are supposed to occur. in the beginning this event queue is empty, and you just define what should be happening right at the beginning. For example, you could say that behavior of A is, put a 1 on this wire after time delay 10, or if it's an airport, the flight has just arrived and it is scheduled for takeoff after half an hour. Okay, so you execute these events, and what an event does is it changes the state, and it may trigger another event in the future, either on the same object like this or on some other object like this. Okay, and it may update the state. So in the beginning this event queue is empty, and when you first execute it, whatever gets scheduled is inserted into this event queue, and this event queue is always sorted based on timestamp, earliest timestamp first. So for example, here this A schedules this event, so this event gets scheduled, inserted into the queue at time 1.81. Similarly, B runs and schedules the event that should happen on A at time 0.1, and so on. Now we have just finished here, t equal to 0, you have finished doing your work. Now what do? You increment the time to what value? How shall we increment the time? We have finished. This diagram shows everything, but imagine we have only finished computing these purple things at t equal to 0, and the queue has, this 0 is done. It has something at 0.1 and something to be done at 1.81. So what shall we do the next time? Yeah, so what we do is we pick the smallest time step in this queue. Anyway, it's sorted. So we pop the smallest things which are scheduled earliest next, and we do them. So when we do this, again it might in turn schedule some more events into this queue, and so on and so forth. We stop the simulation when there is nothing in this queue, or when our time limit is up. Okay. And what is an event? It might change the state of this object, or it might trigger something in future, or it might trigger something. So for example, aircraft lands, it will schedule something when it should take off next, and it may schedule some other events like deboarding should start and some other things, right? So this is the event-driven approach. If you notice, this is taking shortcuts in time. First jump was at 0.1, next jump was directly at 0.9, next was at 1.81, and so on. It's taking shortcuts in time. It's not incrementing slowly, which is good, right? But if you notice here, the time can be anything. The time delays can be anything. It doesn't mean that time has to be integer valued. Whereas here, all things happen at some integer multiples of some delta t. Okay? So time increments are fixed. Here they can be anything. So it's good, right? So what is the problem with these kinds of simulation? What do you think? Yeah.
We need to store large amount of events in the queue.
Okay, so potentially this queue could become very large.
And how do we even know where event 4 will happen, like under A, under B, under C? That can be a problem. How do you know that it will happen? Event 4 will be under A or under B or under C?
So events, if you think of an object-oriented program, an event is what change should happen. Right? For example, it increments some counter in A, B, or C, and it will also store the object where it should happen. So all the necessary information should be there in an event. Okay. So what process created the event, which object is it supposed to modify, and what future event it is supposed to trigger. All that information has to be packaged into a object called an event. Okay. So when we execute it, we know precisely what to do. Okay. So this is the event-driven approach. Here, you can approximate systems like this to do this. The problem is, imagine in your system something happens at 1 millisecond. Most of the things happen at 1 millisecond apart, but there is that one thing in the system that's working at 1 microsecond. So what will be your smallest delta t? 1 microsecond. So simply you are incrementing time every 1 microsecond. Most of the things are happening or changing only at microsecond boundaries, but millisecond boundaries, but you're updating it microseconds. That's not great. You could do something like this and take shortcuts in time. So what happens is VHDL, Verilog, System C, a lot of the network simulators use this event-driven approach. Cycle-based approach is good if anyway there is a clock cycle in your system. Everything is happening at these time steps, So it makes sense to use this because it's simpler. There is no event queue. What do you do here? On every clock cycle, just execute A, B, C, increment time, execute A, B, C. Simple. Is that all? Here we are modeling some sort of interactions. What if there are some interactions here? So there could be some interactions, right? For example, A's output may be going to B. And so in the next clock cycle, B's state change should depend on its previous value and the output that went from A to B. There may be some interaction between these things. So now, how do we parallelize simulation execution? And do we really need to? Right? So here, to set the context, this is an example in computer architecture research. Typically, we have huge models, city scale. I mean, city scale in the sense if you are thinking about an architectural model. In a city, there are so many streets and buildings and so on. It's a multi-core system. You have lots of components, okay, cores, interconnects, caches, or if it's a SOC, it will have other kinds of components there in memories and so on, converters, sensors. So we have a model of this system, pretty complex, and it's not just that this is complex, but often the benchmarks are also complex. In a computer architecture research, basically benchmark could be a long program which is representative of what real workload will run on the system. So you want to run this program on these cores and sort of measure what is the performance. And this program being representative of what will actually run on your mobile phone, for example, or your laptop. So it's called a benchmark set. Okay? And you'll have performance metrics like what was the average throughput, how many jobs could be done over time, total execution time, how much was the utilization, energy, errors, and so on. Right? Now, so this system is complex, it's huge in size, requires a long simulation time, and the benchmarks are long. Okay. So the good, the bad, and ugly, the systems are getting larger. Why? I mean, multi-cores are getting very common now. So obviously somebody is designing them. To design them, you need to simulate, right? Before we put something into hardware, we do need to simulate and characterize it. The systems we are trying to build are getting bigger. So consequently, the models are getting bigger. If you want to simulate a multi-core system, on a multi-core system, a simulation runs orders of magnitude slower than the actual system. So it may take you days to simulate a benchmark running on the model of a modern multi-core system, which in reality would take a few seconds. It would take days to run a simulation. And then what is the problem? Now this days means any change you want to evaluate the cycle time to make the decision is days. The good is that the systems on which we are running these simulations are also getting better. So you will have many cores, right? You will have GPU systems, clusters. Can you throw more hardware to speed up your simulation? We would want to. The ugly, there's something fundamentally sequential about simulation, right? If we could parallelize, we would. And we do, but it's a little non-trivial, it's not very easy. So the obvious thing is, if we have lots of machines or parallel cores, then we could do multiple simulations in parallel. So this is obvious. So if you are doing design exploration, let's say what value of a parameter in the system gives you the best performance. Is it 4, is it 5, is it 6? You could do these 3 simulations in parallel, and then, so it will just speed up your design exploration. So this is obvious. So design exploration can still use parallel systems, but sometimes a single simulation run can be the bottleneck. So even if you can do things in parallel, your single simulation run could take days. And the opportunity is that your model is very large. So can we partition the model and speed up the simulation? Divide the model, half of it runs here, half of it runs there. Use multi-cores and speed up the simulation. The not so obvious is when you try to just parallelize it, there are issues. One is maintaining causality, we'll see what this is. Making sure that execution is deterministic. What does deterministic execution mean? Every single run with the same setting should give the same output. Even if your system is stochastic, if you fix the randomization seed, it should give the same output. It should not vary depending on the time of the day, which core ran faster, there should not be race conditions and so on. So we really care about deterministic execution, and obviously we require good speed ups. If using twice the number of cores makes the speed up just 10% faster, that's not worth it, right? We need good speed ups. So how do we do this? So if you look at the algorithms, the two algorithms, right, what can we do to parallelize them? Let's take this part first, right? This is all happening in sequence, right? We are running time ahead from 0 to something. We have this event queue. How do we parallelize it? Okay. Now assume that your model is very big. You divide it into 3 parts. Let's say they are A, B and C. So A, B, C are not just components, but they are parts of the system. If we do this, can we put A on one core, B on another and C on another core? Okay. What about this single event queue? Let's distribute this also. Any events related to A will go here, any related to B, and so we split the event queue also into 3 parts. Now the problem is there is some sort of interaction here. Supposing we start them off to do their work independently. A starts its work, keeps running, B starts its work and so on. What happens is, assume that A is slightly faster and runs ahead in time. It finishes this computation. Then the next one it schedules is here. So it increments to time 1.81, does this work and so on. Meanwhile, B is a little slow. Why B? The core on which it was running may be slower or maybe doing some other work. Then it finishes this, and now it schedules some interaction on A at time 0.1. But A has already moved ahead to time 1.81. So this is a problem, right? A should have done something with the message from B at time 0.1, but it has already gone next to time 1.81. So what should it do? Okay, you have allowed them to execute in parallel, but now A has gone ahead and it is a causality issue. It should have done something earlier, and that potentially could have affected what happens later. So there is no just like, okay, you can't just compute the event later on. You have to roll back in time or not allow this to happen at all. So there are basically algorithms to do this into 2 main categories. One of them is called opportunistic sort of one opportunistic kind of algorithms. What they do is they allow this to happen, run ahead, but later if a message arrives that should have happened before, you roll back all the changes that you made. It's pretty complicated because it's not just the changes you made, but you might have sent some messages to others which have to be undone. How do you undo those messages? You send them some undo kind of messages and you roll back the state. If the state changes were very simple, like increment some counter, to undo it is to decrement the counter. So very straightforward. If you have a event, then there is an unevent, very simple to calculate. If you have a message, the unmessage is also very simple. So for some systems like transport simulation and so on, this kind of thing makes sense, or simple queuing systems, because it does give good performance when these things happen rarely. You allow everybody to go ahead at their own speed. If there is a causality issue, roll back. If the rollback is cheap and very infrequent, it makes sense. But imagine you're simulating a computer system and state changes are very complicated. Rollback is impossible to calculate. Okay. Then what do we do? So there are conservative approaches where you say, okay, let everybody go ahead a little bit, then everybody sync up, make sure you're all on board, then go ahead a little bit and so on. So these classes of approaches are called conservative approaches. And here, so for example, let's say you know that these are flights going from B to A, and the smallest delay of any flight is 1 hour. So A is not going to get any change from B after T0 at least till 1 hour. No change is going to come from. If you know something about the system beforehand, you can use that fact to say, okay, now everybody can run ahead for 1 hour's worth of simulation. No messages are going to come in that 1 hour. After that, we can sync up and so on. So we have these 2 classes of approaches. So conservative and optimistic. Okay. What about time step if you want to parallelize it? This is used for continuous as well as discrete event models. And a lot of the models, if you can assume like network models, computer architecture and so on. You are doing simulation like this. How do we parallelize? It looks trivial, right? Why don't we put A on one core, B on one core and C on another core? Okay. Now let T0 all of them run. Wait. How do we wait for multiple work threads to sync up? It's called a barrier in a shared memory system. We put a barrier or wait for them to finish. Then they all run for time equal to 1, then they all run for time equal to 2 and so on. This is one way to do it, but it's not so trivial because now what happens if there are some interactions? For example, assume that these are some blocks in your computer architecture model and the output of A goes to B, so B's state change depends on its previous value and something coming from A. And B also depends on the previous value of C. And the current value of B determines the new value of C. Some such. Do any of you know what are these kind of systems called? The systems where in a block its value only depends on the previous clock cycle value of C, these kinds of interactions, versus the systems where it could depend on the current value in this clock. These are all clock systems. There's a clock happening. There is a term for these two systems.
Causal, non-causal?
No, they are all causal. They have to be causal. They have to be causal because there is a causality. Okay, it means what A is happening, something is happening that is affecting B at the same time, and what happened to C in the previous cycle is affecting B, and whatever happens to B is now affecting C. You can just build any circuit using some gates that does this, right? So two kinds of systems or two kinds of finite state machines, for example.
Time dependent.
Yeah, Mealy and Moore, that's right. So perfect. So which is which? Do you remember which is which? Okay, very good, very good. So Mealy is a system where your current thing could depend on the current value of something else. Okay. Moore is where it would depend only on the past values of the other component. So it's an assumption on what basically you allow in your model. So this is deterministic, by the way. Okay, we are not talking about deterministic, non-deterministic. Yeah, this is not. This has to be deterministic in the sense of computer architecture models. Okay. So if we have this, how do we execute? Because I mean, if we have to do it, you must run A first. Then using that you must run B and the previous value of C, and then using that you must run C. So you have to first do A, then B, then C. So how do you get parallelism? I mean, how do you do anything in parallel at all, right? So what can we do? And we don't know this communication structures beforehand, or maybe we do know that beforehand. We might know what is connected to what, or they may be dynamic. So what shall we do? By the way, this approach is also used in epidemic simulations. Simulation of how, let's say, COVID will spread or something like that. Simulate every day. Or it's used for traffic simulations and so on. So a lot of simulators use this approach. So one way is, okay, so here for example, A connects to B, B connects to C, and C also connects to B. There is a loop. So the order of execution among components will matter in every clock cycle, right? We must do A first, and then B and C until there is convergence. Okay. Even with this, if we try to parallelize it, then there may be race conditions when reading from this shared communication channels. For example, if writing to it means putting something on that, and reading means removing something, if the removing happens first before the writing, then there is some space to write. If the writing happens first, B tries to write, the C has not yet removed, there is no space, it's not able to write, you get a different result. So based on which thread actually ran, you may get different results, the race condition. So we want to avoid all of these, right? Simulation has to be deterministic, and the same result when you run a sequential simulation versus when you parallelize. We want the same results. If you are getting a different result when you parallelize, then that's not good, right? It's making mistakes. So what could we do? One way is to do a dependency analysis of the whole model. What is connected to what? And then execute them in that order. You'll get a graph. There may be loops in the graph, but you try to determine some order in which we execute every clock cycle. But that limits parallelism, right? If you have to execute in some order, how do you get the benefit? If you have loops, we may need to execute multiple times till convergence. Another approach that is used by VHDL or Verilog is a two-phase execution mechanism. Of course, they use event-driven, they don't use this. But what it could do is basically have this two-phase execution mechanism. Everybody evaluate their output but don't apply, then wait, then everybody apply their output, then wait, then everybody evaluate their so this is a two-phase execution. So every sort of clock cycle is divided into two phases. One where you just compute, do not generate output or do not trigger anybody else, and wait. When everybody has done that, everybody apply the outputs and so on. So how will that help? So it can help in certain situations. So we'll see how this idea, this idea is used by some frameworks and tools. So with that context, I just want to discuss this framework called Sitar. It's a modeling framework that we have developed. The reason was that we were doing some computer architecture research, and there were a lot of frameworks that do event-driven. There were very few generic modeling frameworks that allow cycle-based modeling. Specific simulators, let's say a network on chip simulator or a memory simulator that people have made, have some approach, but they are not modeling frameworks. That is a specific simulator for modeling that. What we want is a framework, a language that can allow you to model things. You can create your models, but that uses this parallel cycle-based approach. And also a lot of the frameworks are not designed for parallel execution from ground up. It's more of an afterthought. So for example, in System C, there is a cycle-based code, then there is a parallel version of System C and so on. But the kind of speedups you get are highly limited because they have not been designed from ground up for parallel execution. So the idea was to make it easy to parallelize. So it's a framework which consists of a modeling language. Basically that language has constructs for describing structure and behavior similar to VHDL or Verilog, and you can embed C++ code. So anything that you have already written in C++ is very easy to port to this framework. You just need to add things about how things are connected and so on. But otherwise, rest is C++. And you can describe behavior like this. Do something in code, then based on a branch, you may enter this branch or that branch. This is not the same as a branch in your programming language. Why? There is a state implied. If you do this code, something, and then there's a branch. If you take this branch and you remain in this branch. So if you wake up every clock cycle, you are currently in this branch. It implies sort of a state you have entered. Different from a if-else in a programming language. There are loops, branches, there are parallel blocks and so on. So the language provides different constructs and a way to describe structure, what is connected to what, how are they connected and so on. And it's very lightweight, so very small code base. So it's open source framework and designed for shared memory parallelism, but currently we are working on making it work on clusters. So basically a modeling language and a cycle-based simulation kernel. It's targeted for systems which are large, otherwise no benefit of, you won't get much speed up. System needs to be large, okay, many concurrent components, having complex distinct behaviors. So this is important because there has to be enough work for every code to do every clock cycle. If that work is very simple, this may not be worth it. For example, computer architecture models and so on. It's good if it should have a static structure, what is connected to what. And it operates in discrete time, so all things are synchronous. And the communication between subcomponents has some delays. Okay. So these are the examples that it is targeted for. Architectural level models, computer networks, clock VLSI systems and so on. So I'm going to skim over the details of Sitar very quickly, but you will find details in these two papers. One is WinterSim, the other one is Simultech, these conference papers recently. So basically we use this two-phase approach. These are systems that it can represent. We make sure that the clocks are divided into two phases. In one phase, every module can only do input. In the second phase, every module can only do output. Okay? Every clock cycle is divided into two phases. And basically you do phase 1, wait for everybody, then do phase 2, wait for everybody. That's the approach. So if that's a true thing, then there is at least one clock cycle delay for every communication. That means whatever has less than one clock cycle delay should all be put inside this component, package it inside one box. As long as they have some delay, you can split it across different boxes in the simulation. You can model 0 delays, but you have to put it within one box. So the two-phase execution algorithm is very simple. Phase equal to 0, run all modules. Phase equal to 1, run all modules. That's it. No dependency analysis required. Okay, and then increment the cycle and run it again. So a very simple algorithm. And how do we parallelize it now? The order in which the modules are run is not important now at all, because you get the same result no matter the order in which you run. So you just split this work across threads, put a barrier. Split this work across multiple threads, put a barrier. This is the OpenMP syntax for doing it. This results in a race-free execution. Why? There is a simple assumption that every communication channel has exactly one writer and one reader. So with this, you won't get any race conditions, because a net is either being written to or read from at any given time, but not both. It will never happen that there can be a race condition. So it's a very, very simple algorithm. So what's so great about it is not the algorithm is very simple, but the language is very rich. So it allows modeling nicely structures and behavior, and has sort of syntax highlighting, debugging support, systematic logging support, and so on. So it's fairly advanced for describing a very large system. This is an example of structural descriptions. The things it offers are very similar to VHDL. You can have generics, loops, and so on. And for describing behavior, you have sort of an imperative sort of thing where you can have code blocks, wait statements, wait for a time or wait for condition. You can have simulation control, stop simulation, continue, pause. And you can have if-else branches, parallel blocks, and procedures. Procedures where you're repeating something again and again, you make it a procedure and call it multiple times. Just like a function, but it has a sequence of steps, and you can have delays in between those steps. So it's an example of something like do something, then if some condition, either do this or do this. If you're here, do something, wait for some time, do something and repeat it sometimes. And when you finish that, you're here. Or you might enter these two things, you wait for something in parallel, and when they finish, do something. So it's very straightforward translation to C++ code. Okay, whatever is the purple thing is raw C++ code here. It is just embedded into two dollar symbols. It's just raw C++ code. So we built this generic multi-core simulation model, cycle accurate model for the cores, 3 levels of cache hierarchy, it's parameterized in a memory. And this was run on a 4-thread system, so we got speed up of 2.2 when running benchmark programs here. And then there are some studies on a large benchmark model, okay, what kind of speed ups you get and so on. So I'll not discuss it, but we get speed ups close to 50x when using 64 threads. When there's not too much communication, when there is communication, then it goes down a little bit, let's say to 30x or something like that. There's a comparison with SymPy and System C performance comparison. So it does better than, much better than SymPy, slightly worse than System C, very slightly worse in sequential execution, and does much better in parallel execution. So yes, so a quick overview of the ongoing and future threads. So related to Sitar, we are building a Python port of this, support for cluster execution, and a unified framework that allows tweaking the execution model whilst the model remains the same. So a framework called UniSynPy. So we have plans to kind of develop this, and porting complex system models to Sitar. So there are some projects going on that are on this. And maybe just pick this to some other research threads. So we have some work in hybrid simulation, co-simulating systems that are discrete, event, and continuous. And this is an example of a framework we have built in Python for hybrid simulation. And supply chain simulation and modeling using graph neural network meta models for speeding up design space exploration and so on. This is work done by a PhD student. He has also built a supply chain library and LLM assisted generation of models in manufacturing systems. So again, translating course description is into executable models with validation in the loop and so on. Some of the other talks also discussed this kind of work where the output is a structured output generated by the LLM and so on. Yeah. So thanks. I don't know if you have run out of time for questions, right?
We can have some questions. Questions?
Any questions?
Ma'am, you said you gave an example if A and B are different cores. What if they don't sync with each other? What if A takes a little more time than B? Then it won't. How will the parallel execution work in that case?
So this requires something called a barrier, right? If you have you used barriers? A barrier is a construct that says wait, everybody must wait till reach here. It's used in operating systems also, right? All the processes finish something and they say okay, everybody should wait at this point before proceeding. So we will need a barrier after every clock cycle here in Sitar.
So it's it will only work for the synchronous model.
Yeah. So
No.
if you don't have any synchronization, then this causality problem will happen. Somebody will run ahead and somebody will.
No. Thank you.
More questions?
So, ma'am, what if there's a what if there's a lot of dependency in your sitar
Model.
algorithm or model? So wouldn't it behave like sequential? Then there's no point of calling it a parallel execution.
Exactly. So that's a good question. What we do is we can cut the model on boundaries where there is some communication delay. If all of the model has communication which is zero delay everywhere, very dense communication and no delay, then this is not a good model. Okay, this is not a good approach for parallelization. What we are assuming is that we can cut the model on things which are, and then the partitioning is done automatically here. We don't need to do some other code that does the partitioning. What happens is the user is required to write a module such that this one delay happens. So anything that they want to communicate in zero delay, they must put inside a module.
So, I mean, there's a fairly popular event-based simulation infrastructure, SST,
Okay.
very commonly used by architects, especially. Have you tried comparing with
No,
that?
no, we haven't done. So
Okay.
it's a good suggestion. I think we can do.
Okay, let's thanks Neha once more.
Small token of thank you.
In the last 2-3 years,
primarily on the problem of novel view synthesis, and the tools that we have been using to solve this problem have also evolved. So I'll first talk a little bit about neural radiance fields, which were popular in solving the novel view synthesis problem, and then move on to Gaussian splatting, 3D Gaussian splatting. And I will look at these problems primarily from the point of view of how you can reconstruct novel views. Yeah. Okay. So I will look at how you can do novel view synthesis, especially when you have very few images available for learning a radiance field model. Okay. So what is novel view synthesis? So imagine an environment like this auditorium here. Let's say you have some images of this environment available to you. Some images have been captured, and you want to be able to reconstruct images from unseen camera viewpoints. Okay, so this is what we refer to as novel view synthesis. It's a fundamental problem in computer vision and graphics, and has many different applications. So the idea is that there are some camera viewpoints from which you've captured images. You know those camera parameters, where those cameras are located and their poses. And from unseen viewpoints, you want to be able to render the images. Okay. Now there are several applications of this. One of this is in cinematography. So modern cinematography, one can think of capturing a scene from any random set of viewpoints, and then try to figure out what's the best way to capture a scene in post-production, right? So if you have images captured from some viewpoints, then you might be able to render the scene from any other viewpoints during post-production. Therefore, it can improve the quality of movies and things like that which you can generate. In fact, this is something, there are already some examples of ads that have been made using these kinds of radiance field models. Another application is in game viewing. So think of a game that you want, that you want to watch from any other viewpoint. I think if you watch IPL on Hotstar or JioStar, it gives you so many different camera viewpoints. Think of just trying to expand that. Will help you do that. There are other applications in telepresence, applications in autonomous driving, applications in robotics, and so on and so forth. Right, so the view synthesis literature itself has been quite very rich. The problem of how do you generate novel views for a given scene. In fact, one of the earliest approaches to novel view synthesis was based on image-based rendering. This particularly assumes that you have knowledge of the depth of the scene. Like for example, in some graphics related content, you might, because you are creating the scene, you might actually know the depth. And you might be able to render views from other viewpoints. There are other approaches to render novel views, those that are based on mesh-based representations. But again, these tend to be very hard to optimize. There are other modern methods based on deep learning that have been developed based on discrete volumetric models. But a major challenge in all these approaches has been to come up with a continuous volumetric representation so that you don't suffer from discrete artifacts, as well as trying to be able to have a small model size for representing a scene. Okay, so that was the motivation behind trying to search for better representations and a quest for neural radiance fields. So today what we'll do is I'll first briefly talk about neural radiance fields, which is one approach that overcomes some of the drawbacks that we just discussed. I will then talk about one drawback of nerves, which is the fact that it requires a large number of input views for training. And we look at sparse input nerve, in particular talk about one of our works, VIP nerve, that addresses this drawback. Nerves in general have a major drawback, which is that they are very slow to train and render. So we look at 3D Gaussian splatting that came up recently, which tries to address some of these drawbacks of nerves. And then we try to study 3D Gaussian splatting again in the context of sparse input scenarios, when you have very few input images to learn a model. And then finally conclude by talking about what are the future directions that one could take in this space. Okay, so the neural radiance fields work was a seminal paper in 2020 at ECCV. and I'll briefly introduce you to this topic, and many of the slides that I'm presenting were presented by the authors in their original work. So what is a neural radiance field? It's a neural network that takes as input a 5-dimensional input, right? So out of these 5 dimensions, there are 3 dimensions that talk about a spatial location, x, y, z, and then you have 2 other parameters that talk about a view direction. Okay, so say think of a 3D position in this room. So you query the network with a 3D position and a viewing direction. Okay, so the viewing direction is say suppose I want an image to be rendered here, and I'm looking, then the view direction corresponds to the ray passing through the pixel at which I want to reconstruct this particular scene. Okay, so this 5-dimensional input is passed as input to the network, and this neural network gives you 2 kinds of output. One is what is the color of this particular object that is there in 3D when viewed from a particular viewing direction. Okay, so the whole idea of in nerves, nerves give you the ability to model view dependent color, meaning that if you view the same object from different viewing angles, your color could change, and nerves lets you model that aspect. And in addition to the color, you also output what is called the output density or occupancy, which tells you whether there exists some mass in a particular 3D point in space. Okay, so if you look at most of the space, it's all empty. Maybe the point on the floor, I mean, there is some mass there. There's point mass on the chair and things like that. So that's what nerves help you learn. Okay, so they help you learn an environment. When you feed a particular 3D point as input and a view direction, it helps you get the nerve is trained, the network is trained to output color and volume density. Okay, so this is referred to as either output density, volume density, or occupancy. It just measures whether there is some mass in space at a given 3D location. Okay. Now, why is this useful? This is useful because by training such a network, I might be able to render a scene from any arbitrary viewpoint. So think of the following. Let's say you want, this is the underlying scene. Okay, so this JCB is the scene that you want to reconstruct. And let's say you want to reconstruct this from many different viewpoints, and say this for example is one of the viewpoints. Now what you do is to render a color at a particular point here is to pass a ray through this pixel into the scene, and then you sample points along the ray. Now each of these points that are sampled along the ray is actually a 3D point, and there is a view direction associated with this ray. So if you feed this 3D point and the view direction to the network, it will output a particular occupancy and color. So it will tell you whether in space this point is occupied or not, which is your occupancy, and it will also give you the color corresponding to the point along the ray. Okay, and then using a combination of the occupancy and the color of all the points that are sampled along the ray, you can combine them using what is called a rendering equation. I will talk about it in the next slide, to obtain the color at a given point. Now once you train a model to learn the scene exactly, so any 3D point that's queried from any viewing direction, you will be able to predict the occupancy and the color. And so by combining points, so if say you want to reconstruct this pixel, right? So then you pass a ray through this pixel into the scene, and then you sample points along the ray, and then for every point along the ray you query the network, and then it will output the color and the occupancy, and then you can combine all of them to output the color at a given point. So I've been saying a lot about combining the colors and obtaining the color at a given point based on the points that have been sampled along the ray. So let's briefly look at how these colors are combined. They're combined using what is called a rendering equation. At the core of it is the continuous model for the rendering equation. So let's try to think of this equation. Let's try to understand what is happening here. So what this equation says, let's try to first understand what these symbols mean. C corresponds to the color. Sigma corresponds to the volume density. It represents whether there is mass at a given particular point in space. This T corresponds to the fraction of light that is emitted from a particular point that actually reaches the pixel. Okay. So say if all of is this amount, this is the amount of light that is emitted from a particular point. This measures how much of that light really reaches the camera or the image plane, and then you add all the light along the ray to get your overall light that is collected at a given pixel. Okay. Now this continuous volume rendering equation can actually be discretized. Okay, so you can sample points along the ray and you can actually get this discrete approximation which has a similar interpretation. So where again you have color of all the points along the ray. This alpha I, this alpha I is somewhat related to how much of light how much of light is emitted by that particular point, and it's referred to as the opacity. And Ti corresponds to the fraction of light transmitted from a given point that actually reaches your image plane. Okay. Now using this volume rendering equation, you can actually compute the integrated color, okay, the color that's summed up along all the points along the ray to obtain the pixel, the color of a given pixel. Okay, so now once you are able to construct this rendering equation to obtain the color of a given viewpoint, then you can train this neural network, meaning the parameters of this neural network, by comparing the color reconstructed by the model, which is what I call as render I of f theta, with the color of that particular pixel that is there in some of your training images. So if you have a large number of training images, you can learn the network to be able to predict the color at every pixel such that it learns the occupancy and color of all the points along the rays accurately. Okay, so by minimizing this loss, you can learn the parameters of this network quite well. Okay, so you have a large number of input views. You try to reconstruct many of these input views using this network of parameters. Questions so far? Is the basic of what a neural radiance field clear?
So can you explain the loss?
Yeah, so the loss just compares the ground truth color. So think of I sub I as the RGB values at a given pixel that you're trying to reconstruct, and render I of f theta is nothing but the color that's rendered by sampling points along the ray, querying each one of those points through the nerve, obtaining the sigma and color, and then using the rendering equation to combine all of them to obtain the color at a given location. Okay, so what is the network? The network is actually a fairly large neural network. It's a fully connected network. What goes as input to this network is simply, for now, omit this gamma of x. You just think of the input as just it being x. Okay, x corresponds to the 3D points, right? So you pass a 3D, you take the 3D points and then you pass it through several layers, a deep neural network, if you will, and then you predict some features from which you can obtain the sigma or the color, and then you also feed the view direction at some point. It turns out that you need the view direction only to predict color. Okay, so the key point in nerves is to note that volume density is independent of view direction. Only the color is influenced by view direction. Okay, so the view direction only influences the color prediction, whereas occupancy is not influenced by view direction. It's just a fundamental property of this environment, and so you don't need the view direction to predict the volume density. Okay, so this is at a high level what the architecture of the neural network is. I mean, at this point when nerves were introduced, this kind of an architecture was somewhat well known. The two key innovations in nerve were really these two aspects. One is the notion of coarse and fine nerves, and the other one is the notion of using positional encoding. Okay, so let me first talk about what coarse and fine nerves are. Yeah.
The XYZ first you introduced.
Yeah.
Is it the position of object or the camera?
XYZ is a point in 3D space. So if you go back, right, if you talk about how rendering is done, you query points along the ray. Okay, each of those points has an XYZ coordinate. That XYZ is what is passed as input.
What is the object?
So you don't know where the object is. You pass a ray through the pixel. You sample points along the ray. For every point in the ray, you query the nerve. And if there is an object at a particular location, you get large occupancy. If there's no object, you will get something that's close to zero. Okay, so the two key ideas in nerves are about coarse and fine nerves, and the other one is about positional encoding. So I'll talk about why you need both these two aspects. Now think of, one of the main issues with discrete volumetric approximations, right, that I introduced long back, was that this whole discretization or quantization can actually introduce errors. right? So, but in fact, at some level, even in our nerve approximation, right, we have indeed ended up quantizing this whole line. And so, one way in which you can address this is by using a smarter sampling of points along the ray. Okay, so normal stratified sampling means that if you want to sample more densely, then you have to sample more points along the ray, which means that you will have to query the nerve so many more times, which will increase the complexity of the rendering process, right? It will slow your whole rendering process down. So in order to overcome that, in the nerve paper, they introduce what is called a 2-pass sampling procedure, where in the first pass you just query the nerve as usual at some sampling rate. You pass the sample points to the nerve, and then you get your estimates of occupancy and color. Okay, so now using the occupancy and the color, you can figure out how you want to combine the colors of all these points, and you get some implicit weights. Think of Ti alpha I as some weights with which you can actually control the color, right? So that kind of represents how much color is contributed by that particular point. Now what that means is that if there's a particular point that is contributing more to the rendering at a given location, then my object likely exists around that location, as a result of which I can sample more points around that location to get a more precise description of my scene. Okay, so you can take the first pass output of the weights that come out of the network and sample more points based on that first pass weights. Okay, so wherever there is more mass, you can sample more points around that location, and then in your second pass nerve, you can use this sampling procedure to get more fine-grained weights for your rendering. Okay, so the whole point of this nerve is you're going to use one coarse nerve where you sample points in a coarse manner along the ray, and then you're going to use a fine nerve where you sample more points around where you think the object exists, and then you use a combination of the two to render your particular pixel intensities. Okay. Now the question that can arise is, why do we need two nerves? Why do you need a coarse nerve and a single nerve? Why can't you train a single nerve with both coarse and fine sampling? The challenge is that, if you use a single nerve, it can lead to misleading targets. For example, if you think of an object here, right, in the coarse stage, if you sample a point along this interval, it has to output any point along this interval, right? So even for example, a point here, because this point lies in this interval and the object exists in this interval, it will have to say that there is occupancy in this for this point, right? Whereas in the fine nerve, you want to say that at this point there is actually no mass. So because of such contradictions, it may be hard to train a single network to model both the coarse and the fine sampling. So that's the reason why you have a separate coarse nerve and a separate fine nerve that you train in tandem. Now the other issue with nerves has got to do with learning to produce sharp transitions. If you think of the world around you, it has sharp transitions of color. So the geometry that you learn should also have to be really sharp. However, the tool that we are using, which is neural networks are somewhat smooth operators. So if you feed 2 points that are very close to each other, the neural network will learn a smooth transition of the output from one point to the other, as a result of which it inhibits the learning of sharp transitions. If you want a sharp change in color, right, or occupancy or whatever, right, that becomes hard to learn with neural networks. So to overcome this, the authors of NERF introduced what is called positional encoding. So the idea is to, if you have a 3-point input, right, your x, y and z, you convert these 3 points into a larger dimensional space, so that because you converted it to a larger dimensional space, even if you learn a smooth function over this larger dimensional space, it will help you, closer points in xyz will be moved to points that are farther away in the larger dimensional space, as a result of which even if you learn a smooth function in this larger dimensional space, it will let you learn sharp transitions. Okay, so that's the idea behind positional encoding that is used in nerves. Let me try to illustrate this with an example. Okay, so let's say you consider 2 points A and B that are very close here, whereas you want the colors output for A and B to be very, very different. Now, if you use your normal encoding, right? X, Y, X and Y. X and Y for locations A and B are somewhat very, very close, right? Because they're closely located in this space. So it's hard to learn a network to predict very, very different colors when A and B are so close. Instead, however, if you now start doing positional encoding, so you represent X, okay, using a combination of sines and cosines. You represent X in a higher dimensional space. Now this combination of now your A and B with this position encoding now look very different. That allows you to map them to different kinds of intensities, which is what you wanted in the first place. Okay, so this is at a high level what positional encoding is. It helps you move points that are there in a lower dimensional space into a higher dimensional space so that they are far away. And because these points are now far away in the higher dimensional space, you can then map them to distinct intensities or volumetric occupancies and so on. That helps you learn sharp transitions, reconstruct high quality images. So these are some of the examples in the original NERF paper. So on the top I have, I mean, as you keep rotating your, as you keep moving your camera, these are the different views that you get. They've all been captured with very little views, but they're able to construct a very rich interpretation of scenes that were not originally captured with the camera. Okay, and there are lots of ablations that they showed in the original paper. So, for example, if you don't have positional encoding, right, you can see that the results are very, very blurred. It leads to poor reconstructions. There's also something about view dependence, right? How you want to model view dependent color, right? So in the model, the color depended actually on the view direction. So if you don't allow for that, then what is the problem? And many of these issues were actually shown in the original work. Okay, so although NERFs are great, they have several issues with them. For example, they're very slow to train and render. For example, every point that is there along the ray has to pass through this really long, really large network with several layers, and you have to do this for every point, every pixel. You have to pass a ray through every pixel, sample points, and every point has to go through this large neural network. That makes the entire training and rendering process extremely slow. There are also other problems with NERFs in the sense that they are sensitive to pose accuracy. They all assume that scenes are static. They don't account for dynamics in the scene. They require a large number of input images for training, and they do not generalize across scenes. You have to train a separate model for different scenes individually. So many of these require attention. A lot of work has been done to address these problems. I'll look at one such issue, which is the notion of how can you train NERFs with fewer images, and this is what takes us to the problem of sparse input NERF. I'll talk about VIP NERF, which is a visibility prior based NERF, and so this is something that we had in SIGGRAPH a couple of years back. Any questions at this point? Yeah.
The training data comes from ray tracing.
So the training data comes from images of the scene that are there. So you have some images that you've captured, and then you try to reconstruct each of those images using the model. And so the training data.
Camera, I mean, they don't
Yes.
come from software.
No, they
How
come.
do you get the images that are in the middle of the object?
So that is something that's latent. We don't have ground truth for that. So this is a view synthesis model. So there is no ground truth to validate that whatever you learned in between was actually correct. But as long as you're able to explain all the images from different view directions and positions, our belief is that you would have learned the correct in latent model. Yeah. Okay, so NERFs work great when you have a large number of input views. On the left is what I have, is where I have shown a dense setup when you have a large number of input views for training. However, if you have very few input views, like a sparse set of input views, then the reconstructions are quite bad. Okay, so you have floaters all over the place, and so on and so forth. Okay, so the challenge is that because you have very few input images, you are not able to constrain the learning well, and there is some sort of overfitting. Actually, in all these scenarios, you will observe that the training images are reconstructed very well, but the test images have severe distortions. Okay, so in the context of NERF, so the whole idea is to somehow constrain the learning. There's a lot of literature on how to constrain the learning. There's this work called DSNERF, which uses depth supervision from what is called a structure from motion model to constrain the NERF training. There's also other kinds of priors, dense priors. The DS nerve prior is actually quite sparse. You have supervision in very few pixel locations. The DDP nerve is somewhat more dense in nature, but it uses a deep neural network to generate priors, and it suffers from its own generalization issues. So when we were looking at this problem, we wanted something that will provide for dense supervision, meaning you want supervision at every pixel location, but you also want the supervision to be reliable. Okay, so we didn't want to use an off-the-shelf neural network and things like that. So we were looking at other kinds of supervision that may be relevant, and in this context, we relied on visibility supervision. So what do I mean by visibility? So let me introduce the notion of visibility. So the idea is that if you look at these two views, right? Okay, so if you look at these two views, you have a primary view and a secondary view. There are some points that are visible in both the views. For example, this point would be visible in both the camera views, and this point would be visible in both the camera views. But there are some points, for example, this point, it's actually occluded in the second view. Okay, so you can't see this point from this view, you can only see it from that view. Now the idea is that if you know that some points have to be visible in both the views according to pixel, okay, so based on pixels, if some pixels are visible in multiple views, then the inherent model should also be able to construct a scene such that that point is visible in both the views. We observed that one of the key reasons why the nerve training was failing in the context of sparse inputs was that it was trying to overfit to the scene and put the objects up so close that each pixel was actually visible in each object was only visible in one of the views, as a result of which when you went to the test views, the reconstruction was very, very poor. Okay, so we realized that this whole notion of visibility is quite important, and this can be used as a prior in an interesting way to constrain the nerve training. Okay, so let me talk about how we obtain the visibility prior. Again, this relies on some notions that have been used in the last few years. This is notion of plane sweep volume. So the idea is that let's say you have one of the images, one of the views here, which we call as a primary view image, and then you have another view which we call as a secondary view image. So the idea is that we try to warp the secondary image at different depths. So you assume that you construct a multi-plane image by assuming that all the pixels belong to a particular depth, and then warp them at that depth and find out for what depths at every pixel would the warped image match your primary view. Okay, so this kind of gives you an idea of, I mean, if for example you're able to find a match, right? If at one of the depths, if you warp this image and you're able to match the other image, it means that that is really the depth of that pixel, and also the fact that this a particular pixel is actually visible in the other view. Okay, so if a pixel is visible in both the views, is when you would be able to warp one of the images at a particular depth, and then you would be able to reproject it to the other view. Okay, so if a pixel is visible in both views, then it means that using camera geometry you can go from one view to the other, and this idea is what we use to figure out what pixels are actually visible. Okay, so the notion of plane sweep volumes, which is exactly what I just described, and the notion of multiplane images is used to figure out what regions are actually visible, what pixels are actually visible in multiple views. So once you've identified what pixels are visible in multiple views, now this is through something that is obtained through something that's independent of your nerve. This is what we call as a prior. You can generate this prior using the notion of plane sweep volumes. Once you've determined which of the pixels are actually visible in multiple views, now you can constrain your nerve to satisfy this visibility. Okay, so for example, this tau dash is your visibility prior. This is coming from the prior that we just discussed. This t dash is a visibility that's computed from the model. Okay, so using your nerve model itself, you can try to figure out if a pixel is visible in both the views, and then you can try to match the visibility obtained from the model to match the visibility that's obtained from our prior. Okay, so this provides a way of constraining the model, where you're saying that if a pixel is visible in multiple views, then even my model should be able to predict that this pixel is visible in the respective views. Okay, so there's a lot of details about how this visibility is calculated. It's somewhat technical in nature, so I'll skip this detail at this point. Also, there's another minor aspect that happens. So if you wanted to predict whether a pixel that's visible in one view is also visible in another view using our NERF model, it would exponentially increase the complexity of the training, and it would actually be computationally infeasible. So as a result of which, we made one more change in the NERF architecture itself, where we said that in addition to predicting the color and occupancy for a 3D point and a view direction, we would also predict the visibility of a point from that particular view direction. You would feed a particular view direction and you would ask for the visibility of that point in that view direction of a 3D point. Now the idea is that if you're able to do this, then you don't, I mean it turns out that using, by training the network to produce this visibility, in addition to the color and occupancy, you can significantly help reduce the number of queries to the NERF that are needed and reduce the complexity. You can go down in complexity from n squared MLP queries to n queries by just making the network output one more parameter, right, that's shared with everything else. Okay, so this helps remove a computational bottleneck while trying to produce this. Yeah.
So how do you determine which point to predict?
Yeah, so the point is that what you have is really pixel level priors. You know whether a pixel is visible in the other view or not. Now what you will have to do is you will have to query array through, you have to pass array through that pixel. For each of those 3D points you query the NERF and you get its visibility. Now then you will have to, just like how you volume render, combine the colors of all the pixels of all the colors along the array, you combine this visibility of all the pixel of all the points along the array, and you now get an effective visibility for that pixel. Now this effective visibility for that pixel that's obtained using the model is compared with the prior that we generated, right, using the plane sweep volume. That is really your prior, and then you ask for these two to match. Yeah. So that's what I said in the previous slide. I skimmed through those details. That's where I said that it's somewhat technical in nature, but that's how you go. What you actually have through the model is you try to predict the visibility of a 3D point, but what you have as a prior is really the visibility of a 2D point. But we have a way of converting the visibility of 3D points to visibility of 2D points, and then you impose a loss when both of them are in the 2D space. Okay, so these are some of the reconstructions that you have. On the left you have DS-NERF, which is a baseline model, and on the right you have the visibility prior model that's able to significantly improve the quality of reconstructions. I think I have another example where this is a comparison with DDP-NERF, which again uses a dense prior, but the prior is less reliable, and the VIP-NERF prior helps you reconstruct much better results. These are some numerical comparisons. I think we've compared with respect to, I think these are on two different data sets with respect to the LP-IPS measure, which is learn patchwise learn pairwise image patch similarity score, and I think we lower the better, and we show that our VIP-NERF model does much better when compared to the other models. Okay, so this concludes the part on nerves. We'll now move on to the next idea, which is so far what we've assumed is that we didn't care so much about this slowness in training and rendering. We'll now look at that issue. And then we'll come back and see how we can again deal with how you can deal with large number of input images. Yeah.
Why can't we send novel images into the diffusion model and view?
Yeah. So now you can use diffusion models. In fact, there's a lot of work on using diffusion models along with novel view synthesis, but you will have to deal carefully with hallucinations and things like that. Here this is purely a realistic reconstruction. There is no stochasticity involved in this. You try to learn the actual scene and try to reconstruct what is there in the scene, right? So if you care about the authenticity of the scene reconstruction, then these methods are better. If you're okay with introducing some small amount of hallucinations and things like that, right, then you can work with diffusion models along with them. So there is a lot of work on trying to use diffusion models along with these kinds of things, but there are still some challenges because in all these applications you need some level of 3D understanding. Current diffusion models are not so great at 3D understanding, and so there is an effort in that direction as well to improve image/video generation with better 3D awareness. Okay, So as opposed to a nerve-based model, so what was happening in the nerve-based model was that you would have a number of pixels, you would pass a ray through every pixel, query, take points along that ray, query the nerve through it, and then reconstruct color and so on. This was a very laborious process. So instead of doing rendering by querying every pixel, so the idea of Gaussian splatting is to use some sort of primitives, and in this context these primitives happen to be 3D Gaussians. Okay, so what you do is you model the scene using 3D Gaussians. So every object is modeled using Gaussians. If it's a large object, you could use several Gaussians to model that object, and you project the 3D objects, 3D Gaussians to the 2D image plane to generate the image that you want. Okay, so now the idea is that somehow you can keep the number of Gaussians required under control and not blow up the size of the number of primitives that you have, and by carefully controlling the number of Gaussians that you have, you can actually iterate through all the Gaussians and render quite quickly. Okay, so this is this kind of rasterization approach helps you render much faster than the pixel wise ray tracing model where you pick every pixel, pass a ray and do volume rendering. Okay, so that's the reason why these Gaussian splat models are much faster. Okay, so let's try to see how you can model a scene effectively using these Gaussians. So the Gaussians have multiple parameters associated with them. One is the Gaussian mean, where in 3D is this Gaussian really located. There are then some covariance parameters associated with the Gaussian. How large should the spread of the Gaussian be? And then there are also some other parameters like whether this Gaussian is really visible or not. If you don't need a Gaussian, maybe you should want to get rid of it. This is where the notion of opacity is useful, and it also helps keep the model size under control. And of course, there are also some parameters associated with the color of the Gaussian for you to be able to render. Now the rendering equation is somewhat similar to what we had earlier in the context of nerves. So it's exactly the same thing. So you have a color and the occupancy associated with that Gaussian. This corresponds to the transmittance, which measures how much of the light that is emanated from a particular point or from a particular Gaussian can reach you on account of all the objects or points that exist before that point along the ray, and that helps you obtain the effective color. Okay, and the occupancy here is a function of the opacity parameter. The opacity here is a function of the opacity parameter that we had, and also where the center of that Gaussian really lies. Okay, so if you're close to the center, you're going to have higher opacity. If you're farther away from the Gaussian, then you're going to have lower opacity. Okay. So the whole point of 3DGS is to initialize your environment with some structure from motion points, and then you would project them using projection equations onto the image plane, and then you would compare your rendered image against a ground truth image. You would obtain a loss similar to what we did earlier, and then do backpropagation to update all your parameters of the Gaussians. One of the key ideas in densification, one of the key ideas in 3DGS is densification, which lets you increase the number of Gaussians in regions where you want it to. So if you have a large Gaussian, for example, with a large covariance and so on, you feel that that can be split into smaller Gaussians. Or on the other hand, if your gradients are saying that the Gaussian has to move a lot, then again you would probably want to clone your Gaussians. Okay, so there are many details in 3DGS which let you split and clone Gaussians, which effectively help you enlarge the set of Gaussians and allow you to model the scene richly. However, in the sparse setup, there are lots of issues. Because you have very few input views, right? This whole splitting and cloning can go on in an uncontrolled fashion, as a result of which, say for example, earlier you didn't have distortions in a particular region, and suddenly some Gaussian appears in some location, and if you don't control it, it can keep on going and create many artifacts. So our recent work talks about how you can control such artifacts by interleaving periods of high densification with low densification. This is some work that we will present in the next month or so at SIGGRAPH Asia. So you can interleave periods of high and low densification, and that will mean that you're able to control many of the distortions. For example, on the image at the bottom, many of these distortions have now gone on the image on the top, which is our model alternating densification. where you control this densification by adding some geometry constraints. Similarly, on the other hand, if you blindly impose constraints also, you will lose out a lot of details which you have lost in this competing method, whereas you are able to recover many of these details in our method. Okay, so again, there are more videos on more comparisons of how our method does better than the others. So I'll just say a few things to conclude this talk. One is that there is a lot of work on, 3D Gaussian splatting has helped you control the training and rendering times, and it has allowed you to render much faster. However, there are several issues that still need to be solved. Sensitivity to pose accuracy is still a major problem. Camera pose estimation is not easy. Many of these assume that you have exact camera pose available, and so when camera pose is not reliably available, then you need to account for that also in the optimization process. For example, dynamic scenes, again, we have assumed that the scenes are static, there is no motion in the scene. So if objects in the scene tend to move, then that also needs to be modeled more carefully using the Gaussians. We've looked at the sparse setup where you want to train with fewer images, so that's still, there's more to be done in that. Also, a lot of our work has looked at how do you train a model for individual scenes. However, there may be applications where I might immediately want to be able to render a novel view given a bunch of input images. So these are achieved through what are called feed-forward models that are very popular these days. So there needs to, but the models tend to still suffer from very poor performance, so there's a need to improve the performance of these models as well. And there's a lot of work where you have all these problems put together, right? You want a model that can generate views instantaneously, it can train with fewer models, it will handle scene dynamics, it can handle pose accuracies, camera pose inaccuracies, and so on and so forth. Okay? So lots of challenges to solve, and a very exciting area of research currently. So I'll stop with this and take questions.
Thanks, Rajiv.
So in 3D Gaussian, what does center exactly mean? Center of gravity, or what?
So it's so Gaussian distribution has a mean, right? So that center is really the mean of that Gaussian. So the assumption is that you have a mean at that location, and then you have a covariance around it, and that covariance decides what pixels in an image around that center get affected by that particular Gaussian.
Okay. Thanks.
Sir, what are the matrices needed to evaluate?
So you're trying to reconstruct novel views. So we use typically image quality metrics like PSNR, structural similarity index, and this learned pairwise image path similarity, so LPIP. So these are the typical measures that are used to determine the quality of reconstructions. Of course, there are other things that you can do to evaluate. Very often you want to construct a video, so in which case you can also use video quality metrics to evaluate the reconstructions.
More questions?
So the input image, like the training data consists of several images, and the model is outputting a 3D construction in the format of a video.
No, so in the case of Gaussian splatting, you would output a number of Gaussians with their parameters, and that's the output of the training. Now say suppose you want to render a novel view, novel image, right, in a particular camera, from a camera that's located at a particular point in space, in a particular view direction, and based on that pose and view direction, you would have to render all these Gaussians to obtain the image in that particular view.
Any more questions? Okay.
Sir, do you also account for occupancy error?
Yeah, so in the sense that the occupancy is somewhat latent, and nowhere in many of these are real world scenarios where the true occupancy is never available. So the idea is that that's why the notion of using large number of input views is important. And if you have a large number of input views, if you learn inaccurate occupancy, then it will get corrected for, because you have so many more constraints. But in the sparse setup is where you don't have sufficient number of constraints, where you can learn inaccurate occupancy, you can put objects in inaccurate places, which is where you need more constraints. If you go and look at one of the examples that I showed, right, where a new Gaussian was getting densified, it was happening because of an occupancy issue. There was an occupancy error. But by doing things more carefully, you can control those kinds of distortions.
If you already had a 3D model of a thing and retracing was
question. I think still I would imagine that ray tracing is all much more optimized. I think the whole benefit of this is that it allows you to learn representations for scenes where you don't have such ground truth. Yeah. So I think if you had, I don't think computationally this would be much faster than running a ray tracing model.
Sir, are sparse 3D module converted into 2D or directly
Sparse 3D meaning? Okay, so if you
ground truth model?
yeah, so when I referred to sparse, I said that you will try to reconstruct a model when you have very few input images available. And once you learn a rendering model, meaning that you learn, say, a set of Gaussians, then using those Gaussians, you are going to construct images which are in 2D. I don't know if your question was whether Gaussian should be learned in 3D versus 2D. In fact,
the ground truth value should be there.
the ground truth is all images. So using the Gaussians, you have to render images. And you will compare the rendered images with the ground truth images to update the parameters of the Gaussians.
Okay, so let's thank Rajiv once again for his wonderful talk. Okay, so you all know the next session is the panel discussion of some of our own PhD students. So while the stage is being prepared, can you all come front? So this is the toughest job for you. Starting from the last row. Last row comes like very first to the very first row. So come front, everybody come front.
Maybe two will be good. Okay, sure. Yes. Thank you for dropping. Your bag and all are there in the lab. Yeah. I wanted to talk to you regarding. Yes. If you have time today, then I will stay. Maybe during the hike. Yes. Yeah, I think this is not needed. So you all prepared? The question is? Sorry? I just sent you. I forgot to send you the email. So maybe I'll ask you first. But you are the pro. You've already done this, no?
Okay, let's feel the front seats. That row. Come. Oh, there are so many. Come. Not one, everyone. I should not send you the personal invitation. Come. Oh, maybe one mic can be here. There is a collar mic also. So I want to see there should be no pocket in the front rows.